Hi everyone. All right, now for this lesson, we're going to be talking about what we call double angle identities. I know previously we talked about sum and difference identities, but now we're going to kind of build on those sum and difference identities and expand that into what we call double angle identities. So as you can see, I really just kind of took the unit circle from the sum and difference identities. I kept the values using a common denominator of 12 and just kind of wanted to build on this. So with double angle identities, we're actually just going to be building upon when we did sum and difference identities. So what's going to happen is we're actually going to reference these sum and difference identities for the double angle identities. So we're going to do a double angle identity for sine. So to start off, I'm going to start with the double angle identity of a sine summation, which if you recall is going to be sine of A times cosine B plus cosine A times sine of B. Now, what's going to happen is in your angles, we're actually going to say if my A value is equal to my B value, how is that going to change your equation here? How is that going to change the setup and the way the equation, or the identity rather, how it actually looks? So what I'm going to do is anytime I have an A and a B value, I'm going to assume they're equal, and I'm going to replace them with an X value. So how that's going to look, so now I'm going to have sine of X and then cosine of X plus cosine of X and then sine of X. Now what I want you to notice is in this first term we have sine times cosine, and then in the second term we have cosine times sine, which is the same thing. So really I want to kind of rewrite this so that it looks this similar or looks the same. So we're going to have sine X times cosine X and then plus sine X times cosine X. Now notice how we have the exact same thing in both of these terms. So what's going to happen when I rewrite my identity when those angles are the exact same is I'm just going to do 2 times sine X times cosine X. So your double angle identity for a sine equation is going to be 2 sine X cosine X. Now, same idea over here with double angle identity for cosine. We're going to do a cosine summation. So my cosine summation is going to be cosine of A, cosine of B, those values being multiplied. And then the summation, we're going to subtract sine of A times sine of B. Now, once again, what's going to happen essentially if my A value is equal to B? So once again, I'm going to replace A and B with my X values since those are going to be the same. So now I'm going to have cosine of X times cosine of X again, and then minus sine of X times sine of X. Now here, notice how we have cosine and cosine, which in this case, when I rewrite, that's going to turn into cosine squared X. And then over here, when I have sine X times sine X, then I'm going to subtract sine squared X. So this is going to be my double angle identity for sine. So actually, let me kind of backtrack a second. So when it comes to writing a double angle, so I'm going to backtrack over here to sine X. The proper notation in which you would write the identity is, because it's a double angle, you're going to do sine of 2 times that angle. So 2 times theta, or whether it be X or whatever. And then that's going to be what's in parentheses. But in this case, you don't have to necessarily write the parentheses. And then that's going to be equal to sine X cosine X for my double angle identity for sine. I'm going to make sure I write these in the correct way. So then down here, if I write this one in the notationally correct way, this would be cosine of 2. I just realized, whoopsies, I'm not being consistent with my variables. How dare I? So if I have 2 sine theta, that's going to be 2 sine theta cosine theta. But if I use a variable like x, then it would be sine 2x is equal to 2 sine x cosine x. So, whoops, shame on me. So just make sure you're being consistent with your variables, as I literally just made that mistake. So over here, we're going to have cosine of 2 theta, which is going to be equal to cosine squared theta minus sine squared theta. So this would be your double angle identity for cosine. Now, the trick with cosine is notice how in the components we have cosine squared theta and we have sine squared theta. So this can actually be broken down into other variations. And when I say that, I mean we can use Big Papa. So we have sine squared theta plus cosine squared theta equals 1. So our variations, if I were to find the variations of these, so I could do sine squared theta is equal to 1 minus cosine squared theta. And then if I were to solve for cosine squared theta, that would be 1 minus sine squared theta. So that being said, down here, your double angle for cosine is going to have a couple variations. So first thing I want to do is I'm actually going to split up the cosine squared theta. So meaning cosine squared theta, or cosine 2 theta rather, I'm going to replace the cosine squared theta with 1 minus sine squared theta, and then minus sine squared theta. So a variation here would be equal to 1 minus sine squared theta minus sine squared theta, which means our variation is going to be 1 minus 2 sine squared theta. So this would be another variation of a double angle identity for cosine. And then we're going to do the same idea. So now I'm going to, whoops, not that one. I'm going to copy and paste this one over here, and now we're going to replace the sine. So with this one, so cosine squared theta minus, and then sine squared theta, I'm going to replace with 1 minus cosine squared theta. So now this is going to equal cosine squared theta, and then over here, you're going to have to distribute this negative 1 over here. So that's going to turn into negative 1, and then plus cosine squared theta. So when I combine like terms, this will turn into, not that, 2 cosine squared theta minus 1. So this would be another variation. That is written terribly. Let me rewrite that. Still written terribly, but you know what? It's fine. So even though we're doing double angle identities, even though we've only technically done sine down here, and now we've only done cosine, but the double angle for cosine kind of gave us a couple other ones as well. So all these identities that I'm boxing, you're going to be expected to know and remember. Now, same idea over here with double angle identity for tangent. So with tangent, I'm going to write down the identity first of the summation. So we have tangent of A plus tangent B, and then that's going to be all over 1 minus tangent of A times tangent B. So what's going to happen, once again, if my A value is going to be equal to my B value, then I'm going to replace it with just a variable x, just to say that they're the same thing. So that means I'm going to have tangent of x plus tangent of x, and that's going to be over 1 minus tangent x times tangent x. So when I rewrite, so this is going to be 2 tangent x over 1 minus tangent squared x. So this would be your identity. So tangent, whoops, I did it again. So I could write it as 2x, or if I want to rewrite it as 2 theta, so I'll do it down here. So I'll rewrite it as 2 theta. So then this here would be 2 tangent theta over 1 minus tangent squared theta. So then this would be your identity. Now, another thing I want to kind of build on, especially for tangent, so I'm going to kind of sidetrack over here for a second. So from the unit circle, when we first learned that, hopefully you remember that tangent of x is the same, dang it, is the same, dang it, let's try this again. Take 3. Tangent x is the same as sine x over cosine x. So I'm going to use this same logic over here for my double angle identity for tangent of 2x. So with that being said, tangent of 2x is also the same as tangent. Y'all, I need coffee or something. Tangent of 2x is the same as sine of 2x over cosine of 2x. So I can actually take my ratios for the double angle of sine and the double angle for cosine and actually just simplify that ratio, and that will give me the same thing as tangent for a double angle. Hopefully this is making more sense. Hopefully what's written is making more sense than what I'm saying at this point, because what I'm saying, I feel like I'm just kind of going off on a tangent almost. Ha 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 ha, tangent, ha ha. Okay, anyways. Now for the practice problem. So what we're going to do is we're going to be given some sort of trig ratio. So I give you that sine of theta is equal to 3/5, specifically where it's going to fall between 0 and... Oh my god. So specifically where it's going to be between 0 and pi over 2. And you want to find the double angle values for sine, cosine, and for tangent. So to start off, if I draw a little coordinate grid, because these are going to be pretty visual, so I would start all of these types of problems off with a coordinate grid. So I know from the unit circle, if I go around, this would be like 0, this would be pi over 2, this would be pi, 3 pi over 2, all the way around to 2 pi. So what this tells me, if I want to be between 0 and 2 pi, nope, not 2 pi, 0 and pi over 2, that tells me I need to be between these two values over here, which means this is an indicator that I'm going to be working in quadrant 1. So I'm going to triangulate. So I'm going to draw a triangle in quadrant 1, or attempt to. And it's not a right triangle, but you know what? It's close enough. I can't draw a straight line, but I have a degree in mathematics somehow. So over here, so the angle that's formed, the reference angle rather, this is the theta value that we're going to be talking about. And then I'm going to label the diagram based on the trig ratio that they give us. So I know that the 3 here, that's going to be the opposite, and then the 5 would be my hypotenuse. So I know opposite of theta is going to be 3, and then I know the hypotenuse is going to be 5. And then we need to find this missing segment down here. So you can either do your Pythagorean triples or you can do Pythagorean theorem to find that missing side. It's really up to you. I know based on Pythagorean triples that this missing side would be 4. It's a 3, 4, 5 triangle. From this setup, what I can do, oh Lord. From this setup, what I can do is I'm now going to find all of my ratios. Meaning I want to find my sine, cosine, and tangent ratios. And then I'm going to use these ratios to help me find the double angle values. So based on my diagram, I know sine of theta would be the opposite over the hypotenuse, which is going to be 3/5, which they also give us. So it matches, it's consistent, we're good. So I know this is going to be 3/5. Now cosine of theta is going to be your adjacent to the angle, so I'm going to say 4, over my hypotenuse, which is going to be 5. So that means cosine would be 4/5. And then my tangent value would be the opposite over the adjacent. So we would say 3/4. Now what I'm going to do is I'm going to use these values to actually help me develop the double angle values. So I know sine of 2 theta is going to be equal to 2 sine theta cosine theta. And I'm going to take the sine theta and the cosine theta values here from these trig values over here that I just did. So to solve this, I'm going to have 2 times sine of theta, which we said was 3/5, times cosine theta, which we said was 4/5. And then you're going to multiply it all out. So in the top, so this fraction over here, this 2, you could say this is the same as 2 over 1, if it helps. So then this would be 2 times 3 times 4 over 5 times 5. So 2 times 3, which is 6, times 4, which is going to be 24, over 5 times 5, which is going to be 25. So my double angle for sine is going to be 24 over 25. So now I want to do my double angle for cosine. So I'm going to do cosine of 2 theta, which cosine of 2 theta is going to be equal to cosine squared theta minus sine squared theta. So when I plug these values in, I'm going to do my cosine value squared. So that's going to be 4/5 all squared minus my sine squared theta value, which is going to be 3/5 all squared. So when I simplify this value, we're going to have 4/5 squared, which is going to be 16 over 25. You can just square each individual number. Then minus 3 squared over 5 squared, which is going to be 9 over 25. And then when you subtract 16 minus 9, that's going to go away. That's going to give you 7 over 25. So I know my double angle cosine value here will be 7 over 25. Why is my handwriting so terrible? And last but not least, now for the tangent one, I'm going to do this 2 different ways, just to kind of give you some options as to what you're most comfortable with. So the one that I personally prefer is I like just doing the ratio of sine over cosine for the double angles, but you could also do your actual double angle identity. It's really up to you. You get the same thing no matter what. So I'm first going to do the sine over cosine way. So I'm going to show you tangent of 2 theta is equal to the double angle value for sine theta over double angle value for cosine theta. So what's going to happen is I'm going to write the sine value. So the sine value, which we already have in the answer, so I have 24 over 25. And then that's going to be over the double angle for cosine, which is 7 over 25. So I'm just going to simplify this ratio. So I have 24 over 25, and then because I'm dividing by this fraction, I'm going to multiply by the reciprocal. So I'm going to leave 24 over 25 alone, and then I'm going to multiply by 25 over 7. Now, your 25s are going to simplify. Those are going to cross out. So what is left is just 24 over 7. Now, here's kind of the caveat. So this is what I call a domino problem. So with using your sine and cosine values, you better make sure or be confident that these are correct. Because if you mess up over here, but you get like one of these right or whatever, then if you plug in the wrong value over here, then the rest of this is going to be wrong as well. So I just kind of want to throw out the word of caution that if you do this way, just make sure that your sine and cosine double angle values are going to be correct. Now I'm going to go ahead and do the same thing over here. So I'm going to do tangent 2 theta, but this time I'm actually going to use the identity. So in the top we have 2 tangent theta over 1 minus tangent squared theta. So when I do this one, so I'm going to do 2 times my tangent theta value, which if I look at tangent, that's going to be 3/4. So I'm going to do 2 times 3/4 over 1 minus 3/4 squared. So when I simplify in the numerator, so 2 times 3/4 is going to give me 6/4, which is going to simplify to 3/2. And then in the bottom, we're going to have 1 minus 9 over 16, which when I rewrite, so that's going to give me 7 over 16, which then I'm going to rewrite. So this is going to be 3/2 times 16 over 7, which I'm going to simplify. The 16 and the 2, I'm going to simplify that to 8 and 1. And then we're going to have 3 times 8, which is 24, over 7 times 1, which is just 7. So no matter what, you get the same thing. It works no matter how you do it. So, nope, having a stroke over here. My recommendation is if you're very confident with your values, I would say just do the kind of quotient property or the quotient identity way. And if you're not too confident on your sine and cosine, then I would recommend just doing the actual identity, and then hopefully you'll get the same thing. Or if you have the time, do it both ways and just double check. See if you get the same thing. So number 2 is going to be very similar. So I would actually say pause here and try this one on your own. See if you get the same thing that I get in a couple minutes. So for this one, number 2, so we're given that cosine theta is equal to 5 over 13, where it's going to be between 3 pi over 2 and 2 pi. So I know based on my little unit circle in my graphic, if I'm going to be between 3 pi over 2 and 2 pi, that's going to put me in quadrant 4. So we want to find all the double angles. So when I'm doing my graphic or when I'm drawing, I'm typically try to only draw the quadrant I need. So I'm just going to draw quadrant 4. So I'm going to draw my little triangle over here, or attempt to. So my theta value is going to be right here. And we're given cosine of theta. So we're going to be given the adjacent over the hypotenuse. So my adjacent would be 5. The hypotenuse would be a 13. And then what you got to be careful about is notice how your y component, we're going to be going downwards. So when you do Pythagorean theorem, hopefully you know that you're going to get a value of 12. But because we're going down, what you have to remember is, well, in this case, my y value is going to be negative. So now I'm ready to do my trig ratios. So I'm going to do sine of theta, cosine theta, and tangent theta. So sine theta is going to be the opposite over the hypotenuse, so we're looking at negative 12 over 13. Cosine theta, we're looking at 5 over 13. And tangent theta, we're looking at negative 12 over 5. So now that I have my trig ratios, now I'm ready to actually do my double angle values. So as a reminder, I like to write down the identities each time I use them. It just helps me remember them more. So sine of 2 theta is going to be 2 sine theta times cosine theta. So as I plug in, so we're going to do 2 times sine of theta, which we said was negative 12 over 13. And then times cosine theta, which we said was 5 over 13. So when I multiply, so I need to do 2 times negative 12, which is going to be negative 24, times 5, which is going to give us negative 120. And then in the bottom, we're going to have 13 times 13, so 13 squared, which is going to be 169. So my double angle for sine is going to give me negative 120 over 169. Now for double angle cosine, so that's going to be your cosine value squared minus your sine value squared. So when I plug this in, so cosine is going to be 5 over 13, and then I'm going to square it, and then I'm going to subtract my sine value, which is negative 12 over 13 squared. Now when I do this, this is going to give me 25 over 169, then minus a positive 144 over 169. So 25 minus 144 is negative 119, I hope. Yes, over 169. So then over here, so negative 119 over 169. Now we're ready to do the double angle for tangent. So I'm going to stick to doing my quotient identity for tangent. So tangent of 2 theta, I'm just going to do the double angle value of sine over the double angle value of cosine. So when I do it this way, so sine of 2 theta is going to give me negative 120 over 119. Nope, negative 120 over 169. And that's going to be over the cosine double angle value, which is going to be negative 119 over 169. So when I simplify this absolutely disgusting and abhorrent looking fraction, so we're going to have negative 120 over 169 times 169 negative over 119, which 2 negatives make a positive, and then the 169s are going to cross out. So this is going to be 120 over 119. So pretty close to 1. little over 1. So this is what a lot of your problems are going to look like, most likely. This is kind of the foundation of what your problems will look like. I will say there's a ton of different ways that we can build upon these, but in terms of rudimentary and fundamental skills, this is what you need to know for double angle. Now down here, so now we're going to simplify the expression using a double angle identity. So you have to really know your double angle identity formulas in order to be successful on these. So once again, in order to use them, you got to know them. So I like to just constantly write them down. So I'm just going to use x this time. So sine of 2x would be 2 sine x cosine x. And then cosine of 2x would be cosine squared x minus sine squared x. And then tangent of 2x is going to be sine of 2x over cosine of 2x, which is equal to 2 tangent x over 1 minus tangent squared x. So people constantly ask me all the time, it's like, how do you remember all these identities? Like, how do I remember the day 1 identities versus like day 6 identities? I'm like, well, I do this. I write them down anytime I use them. I just constantly am writing them down. So that's really my kind of secret way to remembering all of them, is just constantly writing them down, constantly using them. So over here with part A, we're going to be given 2 sine 75 cosine 75. So look at the setup of your identity. So if I have 2 sine of an angle, cosine of an angle, that looks very similar to sine of, or a double angle sine identity. So what this is going to turn into is, I know this is going to be sine of 2 times the angle that's being referenced, which would be 75. So what's going to happen is this is going to turn into sine of 150 degrees, which is on your unit circle. So sine of 150 is the same as sine of 5 pi over 6, which I like to think in radians personally, which that is positive 1/2. So similarly over here with cosine, well, we have cosine squared 15 minus sine squared 15. So I can recognize and look at this one and see, oh, well, it's cosine squared minus sine squared. That's a double angle for cosine. So with this one, what that tells me is I'm going to be doing cosine of 2 times the angle in question, which is 15, which means I'm doing cosine of 30 degrees, which cosine of 30 degrees is the same as doing cosine of pi over 6, which is root 3 over 2. And last but not least, now we kind of switched over to radians. So hopefully you can kind of distinguish that this is a tangent ratio, hopefully. So I'm going to follow kind of the same idea. So this is going to be tangent of 2 times my angle in question, which is going to be pi over 8. So when I do tangent of 2 times pi over 8, that's going to turn to pi over 4. So tangent pi over 4, which is 1. So, Merry Christmas.